Okay.
Okay, now I can hear you.
All right. Well, yeah, we have Yael speaking to us about the Toric project. So please take it away.
Great, thank you. Okay, so today I would like to report on a project that took place between 10 and 6 months ago, which is on Tory varieties, which it tended to be on Tory varieties, but ended up being about something completely different. So this is joint work with Michał and Andrew, who are now both in Lyon and Imperial College London. So, oh, sorry, I'm not taking. Okay. So I would like to explain a bit what the objects in this in my talk are going to be. So I want you to understand the key point is that we are going to study geometric spaces using algebra. So this is the whole theme of algebraic geometry. And by algebra here, I mean things like groups, rings, modules, algebras, which are basically just rings again. And on for the geometric spaces side, I'm going to care about like topological spaces. And actually, I'm not going to care about manifolds and varieties. All I will talk about is schemes, the very last point. So what is a scheme? So a scheme, very simply, is a space that locally looks like the zero set of some polynomial equation. And and the variety is pretty much the same, but we add a few non-degeneracy conditions. I will not talk about varieties because, as Kevin rightly pointed out in some Zulu discussion a while back, nobody really seems to agree what a variety is. So I took a few excerpts because I thought they were quite funny. And so maybe a variety is at least over an algebraic closed field, but then it turns out Michael Scholl didn't want that, or maybe it should be. Well, anyway, this is a whole discussion. I thought it was really fun, and Patrick, who's the audience, concluded by saying that actually, yeah, that was a pretty good demonstration that we should not talk about varieties. So schemes. Typical schemes could be like the circle in the complex numbers, or they could be some elliptic curve, which I've drawn out as the zero set to some polynomial equation. And in general, schemes are complicated, and we want to understand them. We want to come up with some good examples that display the general behavior of schemes without necessarily being impossible to compute with. And in the literature, one such class of examples, which is surprisingly broad, yet very well behaved, is toric varieties. And so toric varieties are, well, I guess maybe I should have called them toric schemes. Toric schemes, they are simple enough that we can compute with them, what will turn out to be convex geometry, and complicated enough that they still show most of the possible behaviors of general schemes. And the project which I want to talk about now is called Toric, and its role here in this picture is going to be to enable computation with Toric varieties. Um, so this will involve proving that certain the operations, the scheme operations that you can do on Toric schemes actually reduce first to algebra, then to convex geometry, which can then be handled using generic convex geometry algorithms, to then formalize those convex geometry algorithms. And finally, what did I say? Sorry, I guess I said everything I wanted to say. And this was written in Lean 4 using mathlib, as one would expect. And I want to talk about the compute part because currently we cannot talk about yes, not Lean 4, not Lean 16s. We cannot talk about the richness part because we do not have enough algebraic geometry in mathlib. Something that we are typically missing would be relative spec, which would enable to do a few more things than we do right now. Okay, so I think I will not teach you so much mathematics here because I think we have a pretty mathy audience. But I want to point out a few things that Andrew, Michał, and I learned by doing this project. And I guess the third point is probably not so relevant for you. Sorry, I'm reusing some slides. But finally, I would like to, at the end, I will outline how the community can get involved for the second part of the project. So, okay, so now I need to explain some mathematics, which I will gloss over rather quickly because it's possibly a bit of a recap for a lot of you. So, okay, I start with schemes. So a scheme is a space that locally looks like the zero set of some polynomial equation. And so I gave you this example of typically the elliptic curve. And the elliptic curve is actually, it should probably contain a point at infinity, right? There's an extra point that I was not showing on my picture. So the elliptic curve needs kind of to be covered by two planes to really see its whole shape. But the circle did not, at least the way I draw it. So I will call a scheme affine if actually I can write it as a zero set of some polynomial equation, like fully, just globally, without having to take patches here and there. Okay. And the typical thing that I will need, the typical way of building a scheme is the spec functor, which takes commutative rings, two schemes. And precisely the schemes that we can construct this way, we call them affine. And what's important about affine schemes is that they are full. The way you can map an affine scheme to another affine scheme is fully determined by the way you can map the corresponding commutative rings. Okay. So building on that, we can talk about schemes defined over some fields. So they are not only just like out there in the void, but we actually, I guess, what we really mean is like, what field do the coefficients lie in? So typically, the two I showed you about earlier were defined, I guess, over even the rational numbers or the integers, but we could talk about like schemes over the complex numbers or things like that. And really, what this boils down to at the level of schemes is to have this canonical map into the spectrum of the base field, which if we talk about affine schemes will boil down to a map the other way around from the field. Okay, and we call them under and over categories. And then on those we can define operations of tensor product, which corresponds to we can define the tensor product of algebras, which will correspond once we've taken spec on both sides to the product of schemes. And am I clicking? Yeah, and finally the last object I need is the notion of a group object, which is a way to generalize groups, I guess. So a group object, I need to have a unit, a multiplication, and an inverse. And those unit multiplication and inverses, so the unit needs to kind of cancel out on either side of multiplication. Sorry, to disappear on either side of multiplication, and the inverse should cancel out the identity on either side of multiplication as well. Okay, so again, not very interesting. Okay, now I can talk about group schemes. So group schemes are simply group objects in the category of K-schemes. And now we can try to think about what they are coming from in the ring world. So we know that affine schemes they come from commutative rings. Affine K schemes come from K algebras. And to complete the picture, we need to have something that actually is going to give us affine group schemes. And the recipe is going to tell us that actually this is Hopf algebras. So what are Hopf algebras? Well, they look a lot like group objects, except that all the arrows are reversed. So a commutative K algebra is going to be a Hopf algebra if it has some map to K, and then there's a co-multiplication which sends A to A tensor A, and finally an antipode which is just an endomorphism of A. And similarly, it will have to satisfy three diagrams that look suspiciously like the ones on the second to previous slide. Okay. So we call them cogroup objects, fine. And at this point, I should mention that all we're going to use to prove this. Oh, I'm not on the. Oh, I am supposed to. All we're going to use about spec to prove that Hopf algebras are exactly the things giving us affine group schemes is simply that we have Cartesian monoid categories, which I guess means that we can take finite products, and we also have a unit object that spec is fully faithful, which means that exactly this thing that you can compute the morphisms between images of spec from morphisms on the original thing. And finally, that it preserves finite products. And this is the thing I showed about the tensor product of of algebras being mapped to the product of schemes. Okay. And then finally, so this is getting into rather close to the toric world. I'm going to call a torus or split torus is any scheme that's isomorphic to the spectrum of the Laurent series in n variables. Okay, and then I can define the characters of a commutative group scheme G as the maps from G to GM which I guess means GM1, so spec of KZ. And the co-characters are going to be the maps the other way around. I'm sorry, I think my headset is running low. Give me a second. There we go.
Okay. And I can compute if I have a character and a co-character, I can compose them, and that will give me a map from GM to GM. And so I can write this as a pairing from G to GM and GM to G to GM to GM. And this is how I will get into convex geometry later, but I will come to it. Okay.
Yael, did you say what is M? Is M a parameter or
Great. Okay.
just some
So
data?
now I can explain how things work out. So we have we start with group schemes, and the group schemes are going to
I hope you find what you're
we
looking
get
for.
characters and co-characters from them, which
Where are
will
you
turn
going,
out to
Barrett? Fast so quick,
finite
please.
lattice. And then a subgroup scheme will correspond to a subspace in the space of characters. And finally, toric varieties, which I haven't defined yet, will correspond to cones in that space. And toric varieties, which I will get from affine toric varieties by kind of patching them together, the same way as I could patch to get an elliptic curve. Sorry, did I say that? I meant M to be. I think I said n equals 1, not yeah, but Michał is trying to correct me. And so toric varieties will correspond to a bunch of cones put together in space, which we call a fan. Okay, and here is an example that that we have actually worked out in Lean, as I will mention later. Yeah, sorry, I can't hear because okay, fine. Yeah, sorry, I cannot hear because I'm plugging in my headset and that's making it not work. So I will take questions at the end, or written questions. So the spectral orthogonal group of dimension 2 over field K is R, the ring, the polymer ring, two variables quotiented out by the equation of a circle. And we can try to compute when this thing is a split torus. And so if we take the field to be the complex numbers, then it will turn out to be GM. And if it's the real numbers, it will not be any GMN for any n. And one way to see that would be to like look at the torsion, look at its torsion characters, for example. Okay, so now I can tell you what we have done. So we've proved that under appropriate conditions, which will in particular be satisfied by spec, we can lift such a functor to the other category and to the group objects, which in our case would correspond to like algebras and schemes over some base, and then Hopf algebras and group schemes. and that we still preserve the fullness and faithfulness of such a functor, and that they stay finite product preserving all the conditions that we started with, plus a few more maybe, minus a few. And this is going to be used in the FLT project very concretely. And on top of that, we have proved that this character-co-character pairing is I guess we've constructed it, so we proved that it is a pairing, and we have also showed that it is perfect when when the group scheme that we started with is a split torus. Then we've constructed SO2 over, I guess I should have written SO2 of K as a group scheme, and show what I've written on the previous slide, that SO2C is a split torus, but SO2R is not. Okay, and now for the pain. So by my description, you can see that I had to deal with quite a few concrete categories. So what do I mean by a concrete category? In mathematics, we usually care about individual objects, like the integers, which will provide with extra structures like addition and multiplication that will make them maybe into a commutative ring. So the picture here is that you have a house and you paint it. My house being the integers and the paint being the multiplication. There are several ways to paint a house, but usually in mathematics we have a preferred color. In our case, it would just be standard addition and multiplication of integers. Okay, but in category theory, and I guess in algebraic geometry as a result, we care about collections of objects. And so instead of having a single object like the integers and coloring it in a way that makes it into a commutative ring, we're going to consider all types together and try to consider all possible ways to paint them into commutative rings. And I guess what I wrote is you buy all houses in all the colors that suit them. And so this is exactly what I will call a concrete category. This is kind of what you get if you take all the possible objects and all the possible implementations of an instance on them. And when you have such a category, it's very important that it's painless to go back and forth between the individual objects and elements of the category. So typically, if you have a commutative ring, you want to be able to get an element of com ring cat. If you have an element of com ring cat, you want to be to get a type plus an instance of com ring on it. And so this was pretty fine for the category of com ring cat, which is the base category. But things started getting more complicated when we went onto the category of commutative algebras, which is, if you remember, what you get if you can kind of consider all the objects with a canonical arrow pointing away from the base ring R. Okay, and finally we also need commutative Hopf algebras, which would be very similar to commutative algebra, so we'll not cover them very much. So the category of commutative rings was in MATLAB, and the category of commutative algebras was not. And why was it not? Simply because we could always use a category constructor under R, and that was what people were recommending to use for a long time. However, under R and an instance of algebra R do not contain the same amount of information. In under R, so this is very simplified, I've skipped all the propositional fields. We have our commutative ring bundled as an element of com ring cat, but okay. And we have a morphism from our base ring R to A. In algebra, instead, we have the same embedding, but we also have the scalar multiplication that we need for other reasons. Typically, that the natural numbers act on any semi-ring or whatever. But this scalar multiplication can be recovered from the canonical inclusion, because or I guess the other way around. Either of them determines the other one uniquely. So even though this extra piece of data that we don't have here is extra, we don't like mathematically it shouldn't change anything. But from the point of view of switching between the bundled concrete category and the individual objects, it's gonna cause a lot of trouble. So you can't because of sorry, if you go back and forth, you will realize that this extra scalar multiplication, you will need to show that it is uniquely determined every single time you do that, and this is really, really painful. So instead of trying to fight that, we've changed the category we worked with. We have explicitly added the scalar multiplication back into the category theory world by creating this com_algcat category, which is the data of a type with a com_ring instance and an algebra R instance on it. And now you will see that this algebra array contains exactly the same amount of information. I guess obviously it contains the exact same amount of information as the instances on the individual objects. Okay. And the obvious thing that we can do, that shouldn't be an equal, it should be an isomorphic. I'm not sure what happened. The obvious thing that we can do then is to show that this category is actually equivalent to the one that was used until then. Okay. And now for commutative Hopf algebras, there is a similar problem that happens, where we could use the general. I guess this is a bit of a like group doesn't exist, but it would be group of op, com_algcat, op, several ops. We could either use generic group objects to define the category of commutative algebras over com_algcat, which we have just defined. But this is again there's again an issue. Well, I guess the issue is different here. The issue is more usability. Because this time we have to stack up a lot of category like a lot of category constructors. Yes, it is a costless category. Thank you, Floris. A lot of category constructors, which make it difficult to actually use. So this is less of a theoretical issue than a usability one. But if all you have is a hammer, everything looks like a nail. Using the same solution end up being quite good enough. So that's exactly what we did. Okay. And so this is the first thing that we learned from this project, is that you can just do this all the time, and this does not cost you very much so long as you keep keep proving an equivalence with the original category. The issue, of course, is that this costs you a bit of boilerplate. Okay, and then something fun, well, maybe not so, is how to prove identities in a generic group object. So a typical thing that we've needed in the project is that we can commute the inverse operation over multiplication, and also multiplication over itself. So in a standard group, that would be A B inverse is equal to A inverse B inverse. I guess commutative group, standard commutative group. And A B C D is equal to A C B D. Okay. Categorically, this is much more complicated, because it turns out that you will have to kind of by hand swap out every single multiplication morphism, reassociate them, and there's a lot of all the coherence isomorphisms that you need to include in exactly the right place. And like morally, we know that those things are true in actual groups, and so we would like to kind of reduce those identities back to those groups. So how do we do that? Well, one way would be to use the Yoneda embedding, which tells us that we can actually embed the category, like any group object, into some morphism, sorry, into some category or some like we can turn it into some pre-sheaf into the category of groups. And then we can verify, because this is just a morph, this is really just like, functors, we can verify any identity pointwise. And this is valued into actual groups. This is annoying in practice because we do not want to actually apply the functor. It's just too much work. And it would be easier if we didn't have to leave the original category at all, if we didn't have to like explicitly transfer all statements. And it turns out that this can be done. Because all we care about really is to evaluate the Yoneda embedding at some specific if you look at how what Yoneda actually tells you. You don't need to evaluate Yoneda everywhere. You need to only evaluate it in like one element. And so you can, if you do that, you will realize that. Sorry, I skipped it. You realize that actually, yeah, all you care about is really like this pointwise multiplication and pointwise inversion on the morphisms. And this works, but this only works if you have Cartesian monoidal categories, where the monoidal this product that I've denoted actually corresponds to a categorical product, which with like the universal property and everything. This is a reasonable assumption, but like mathlib being mathlib, would like to actually generalize this away from the well, we want to generalize it as much as possible. And it should be true in an arbitrary monoidal category, or I guess braided monoidal category or whatever. And but that requires more work. We cannot just use Yoneda. So the idea that we got there is that actually those precisely those like associators and commutators that form the coherence at each level of in the identity actually you can unravel them and they will precisely prove your identity. So here's a oops, sorry, I skipped too much. And so we actually have provided, we actually wrote a tactic that does exactly this, which can be accessed as a mon toto. Sorry, I think I should have written it on the slide. I forgot. Okay, and finally, a few words about examples. So we proved something about the characters and co-characters, and something else about the special orthogonal group. And doing this, we actually discovered a few things. So one, we had a few definitions that were slightly wrong. They captured most of the content of the mathematics, but not quite, and that actually showed us quite a few. It uncovered quite a few issues with our definitions, and they made it very clear whether the code that we had written was actually usable by humans. And finally, they uncovered a few missing lemmas and definitions that we did not have because we didn't need them theoretically, even though they would be useful to include in mathlib or at least in Torek. And okay, so the two examples I mentioned are the characters and co-character pairing and SO2. Okay. And very concretely, that the character co-character pairing is like maybe the prototypical example of how to reduce the hard algebraic geometry nonsense to like easy convex geometry. And that resulted in two things. One, in the linear algebra part of MATLAB, we redefined pairings and perfect pairings to be like a bilinear map along with some predicate rather than a single bundled object, because it turns out that we never want to operate on the space of all on the set of all perfect pairings. And secondly, and this is maybe more important, we realized that the diagonalization functor, which sends a monoid, not a group, a monoid to a monoid scheme, was actually the important object. And this is something that in textbooks is not mentioned, and instead they kind of walk around it in various ways to accommodate for the fact that they don't have this object. And that was a major simplification to the general proof strategy. And finally, we did try this Yoneda without Yoneda approach, which turns out to work great. It automated goals that were previously untractable. Okay, and finally, SO2. We checked that with this example, we checked that our definition of a split torus and also of a torus, which I didn't define, but for those of you who know, you know, is correct, or correct enough to prove the things that we care about. And when I say, well, I guess correct enough, I mean here that actually it's not as general as I would like it to be, but yeah. And okay, and more things. Okay, and finally, I want to like conclude on why exactly we took toric varieties as a project. So my the personal reason I did it was that I had many people around me who were interested in it, but I post-justified it by saying that actually this was a great way to take very disparate parts of MATLAB, namely convex geometry and algebraic geometry, and kind of like force them together. And it turns out that this is actually also useful for also projects like Fermat's theorem, but also like a lot of bits here and there of convex geometry that are done by different people who like never talk to each other enough that things came out of it. And in a similar vein, it really like headed the convex geometry efforts. At least the ones not the ones by Joseph Myers about Euclidean geometry, but like kind of the other ones. They truly headed them towards like a concrete application that's not just convex geometry itself, not convex geometry for its own right. And of course, we want to work out examples of varieties. And although that has not happened yet, we hope that examples will come along. And okay, and finally, like a few here are a few things that I would like to see formalized, and I will not go into them because too complicated, and also I think I'm out of time. I would like just to mention that there are now 3 projects, not just one, that are relevant to this effort. So this is the main one. This is the one that's hosted on my GitHub, Toric. And what I've told you about in this talk is this first phase about Hopf algebras and affine group schemes. And what the future goals I have are like about actual toric varieties and on the convex geometry about fans and how to make them correspond. And finally, to compute on toric varieties. And the second big input, apart from the phase 1, is polytope theory, which is now being handled over to at this repository by Olivia Röhrig and Martin Winter. And as a prerequisite, because the phase lattice of a polytope turns out to be an abstract polytope, which can be studied axiomatically, there is a third project, OV/abstract polytopes, to do exactly that. Okay. And I would like to say that those objects are technically open for collaboration, but they are not at the lean writing stage. Like now, what's needed now is to make way into the thinking of how to formalize things. Typically, convex geometry is not hard to formalize, but because we want to do it in the right way, we're gonna have to really put together all the ideas into a coherent whole that can be used not only for our application but for others as well. And so feel free to message me or Martin or Olivia, Zolip, and thank you for listening. This was also due to a few people who see themselves on this slide. Cool.